Alrighty, welcome to Infinite Geometric Series Part 1. And what I've done, I'm just showing you an example here. This is a geometric series, because what we're doing is multiplying by 1/2. But instead of saying it stops after 10 or 15 or 20 terms, this one goes on forever. And the question is, can such a sum even exist? I mean, if you're constantly adding to it, shouldn't this thing just grow forever? Well, let me just show you by looking at some of these partial sums. Like, okay, S1, we know that's just going to be 10. Okay, then let's look at what if we add the first two terms together. Well, yeah, we get 15. Then let's add the first three terms together, and we get 17.5. Okay. And what you can see is it's growing, but it's not growing as fast anymore. Now you're just going to have to trust me with all the rest of these numbers for now, because I did these earlier on the calculator. But what I'm doing is I'm just adding together these terms, and yeah, it's not really growing that remarkably fast. In fact, it's kind of slowing down quite a bit, isn't it? We've got a 19.6875, and there's a lot of decimals to write out here. I'm getting a little, I think I'm going to end with this one here. So 19.84375. Okay, so what do you think if we were to keep going here and we go on forever? What would that sum, what does it look like it might grow towards? I think you'd probably guess it looks like it's steering towards 20. And you'd be absolutely right. And see, what happens is, yes, we're constantly adding numbers to this, but the numbers that we're adding are just getting so small, they have almost no great impact. You know, it's not like it's uncontrolled, crazy growth. So what happens here is when the sum actually exists, this is what we call converging, or a convergent sum. So this series, I guess this is how we would describe it. This series converges because it seems to actually have a sum. If, on the other hand, if it didn't have a sum, then we would say that it diverges. And that just means that it does seem to have uncontrolled growth and it goes crazy. So this is no sum exists. Okay? So just so you got the terminology straight. All right. So how do we actually know what's going to go on here? Let me just show you an example of a divergent sum before we abandon that. Okay? I'll just clear the screen here and just show you. If you had something like this, say you had a 10, but now we're going to multiply by 2 each time. So now we're going to have 20, and now we're going to get 40, and then 80. And you see how these numbers are they're getting wild? They're getting bigger and bigger. Okay, whenever they start to keep getting bigger like this, that means it's going to diverge. Okay, it's only when they get smaller that they converge. So here's the rule in this whole business of will a sum exist or not. It basically depends upon your common ratio R. If R is less than 1, okay, now think about it. You know, here the R value is 2, right? And they keep getting bigger. But if it's less than 1, or at the same time, R can be negative, but it's got to be a fraction. So we're talking about fractions here, between -1 and 1. And if that's what your common ratio is, then the sum exists. Then the series, this is the fancy way of saying it, then the series converges. Okay? In other words, a sum exists. And that's because the terms keep getting smaller then. And so that's what you want to look for. That's the rule, so that you know you actually have a sum or not. All right, next thing we got to do is we got to develop a formula. So I'm going to clear the screen and show you what we're after here. Okay. Now, the only formula that we have so far for anything that has to do with a geometric series is this one. So we're going to actually build off this formula here. Okay, remember this guy? Well, this is a pretty handy guy here, but anyway. All right, so that's our formula. What I'm going to do, we're going to let n grow to infinity. To infinity and beyond. That's where n is headed, okay? So n is off, getting bigger and bigger and bigger. And we need r here. R has to be a fraction between -1 and 1. Now you notice we don't let it equal 1. You can see why, because then you'd have a 0 as a denominator, which would be trouble. Anyway, so this is the situation here. Now I'm going to try and work with this formula and see what I can deduce. So let's start off by splitting up the top here. Okay, so I'm going to go a over 1 minus r, and then I'm going to have, actually, yeah, I'll do 2 steps here. So, well, I'll sneak the other step. You know what? I'm going to backtrack here. Let's just clear this out. I'm trying to do 2 steps at once, and that's always dangerous. Let's first get rid of the brackets. So I'm going to multiply out the brackets. So I've got a minus a times r to the n all over 1 minus r. Now I'm going to split it up. So I'm going to take this a here, the first term, over the 1 minus r. And then I'm going to go minus, so minus. I'm going to put all the second stuff on top here, a times r to the n, all over 1 minus r. Okay, now I'm going to rewrite this thing a little bit. I'm going to leave the first part of this alone. That one's pretty basic. Now, what do we got going on over here? I'm going to write this as a over 1 minus r. And then I'm going to times this by r to the n. So the big thing that I've got to try to analyze here is this whole r to the n business. Now what's going to happen here? So this is the guy I have to examine. Okay? Now let's say we pick, just to kind of get a feel for this, let's pick some r value, like say 1/2, some fraction. Okay, so if r is 1/2, and remember, n is getting bigger and bigger. So if you tried some number, like I even tried putting in a pretty big number that's not even that big. But if you put in 1,000, I could fool the calculator. I put in 1/2 to the 1,000 and I got 0. Okay, this number gets so darn small that I actually fooled the calculator. Now to see why I'm fooling the calculator, well, you know, let's say you start off with 1. You get 1/2, and that's not that big. But then let n get a little bit bigger, so put in a 2, and you get 1/2 times 1/2, so you get 1/4. Well, it's gotten smaller. And you can see the bigger the exponent gets, the smaller the whole value gets. So this turns into 1/8. And you can keep going like this, but you see what's happening is this whole thing is going to keep getting smaller. So eventually here, I was, like I say, I fooled the calculator. So if n is getting bigger, which it is, it's going off to infinity, that means this whole thing here is going to become 0. And 0 times whatever this is just disappears. So you're left with just this first fraction, a over 1 minus r. And all the rest of this has become 0. And so guess what? This is your formula. And usually we don't put an n because it's infinite numbers. And you say, you know what? That sum equals a divided by 1 minus r. And that's all there is to it. So it's pretty easy, actually, little formula. It's one of the nicer formulas, and I'm going to come back and use it in some examples.